All right, so let's get started. Today we're going to do a review for the exam. So no more new topics that covering in this semester. But first, let's talk about the homework briefly. So the homework was due yesterday, but I guess a lot of you are using your late days, which is cool. Was everyone able to get a reward that got above 25% accuracy? Okay. So did anyone get in the 40s?
That's not consistent.
Not consistent, but you had a run in the 40s. What about the 50s? Anyone? How much was yours? 76. Wow. All right. Anyone get higher than 70? 60? Okay. Anyone? What did you do to get 76? Okay. Out of curiosity, did your generations after that, were they like grammatical, or did they look like real? Oh, okay. Okay. Well, good job. 76 is great. How long did that take? Okay, not bad, not bad.
It's like 0.25 per second for my experience, I think.
Okay.
Yeah.
Yeah, I spent a long time trying to make this homework work on the free collab, and every time, like, it would just cut out at, like, if you wanted to do multiple rewards, it would just be like, okay, your runtime has disconnected, you've timed out. So, luckily, Collab Pro is a little bit better, but still not great. Yeah.
Yeah, I did my homework over like a ton of different collab runtimes, so some of the stuff in there is not that
That's fine. But even with Collab Pro, you had to do that?
I mean, cause I did it over multiple days.
I see. Okay, yeah.
I didn't.
Right. Okay. Any other thoughts about this homework? Yes.
They didn't accept my ID, so I couldn't get Collab Pro.
Okay, yeah, I'm sorry. Did you still manage to do it?
I mean, I bought Collab.
Oh, sorry. All right.
Without Collab Pro, you can work.
I know you can work, but if your reward doesn't work the first time and you have to keep doing training, like eventually it'll time out, which is annoying because it'll.
Not for you.
Not for you? Okay.
Yeah, I tried multiple times, it works.
Yeah. That is totally fine. Yeah. I unfortunately cannot assume that everyone has a GPU. Although, there's a recent Twitter post with like each university ranked by GPUs per student, and I think all universities were below. Oh, no, it was like grad students per GPU or something. No, sorry, GPUs per grad student, and all of the universities were below 1, and everyone was like, oh, well, the ideal ratio would be above 1, which, of course, it requires like millions of dollars to accomplish that, but.
Especially with how high GPU prices have gone in.
Yeah, it's like,
the realistic expectation.
Maryland is not great on that front.
What do you mean?
Like in terms of number of, it's not just GPUs, it's like a H100 equivalent GPUs per student. All right, great. So let us start our exam review. So I'm gonna first just review the logistics. Things are pretty much the same as the first exam, but wanted to highlight a couple of changes as well. Okay, so first of all, the exam has already been written. Surprisingly, I am organized enough to do this before the day of the exam. It has roughly 40 questions. Currently it has 40, but we are going through and trying to assess if that is too many. We might cut some if it turns out to be too long. As I mentioned multiple times in class, the exam will primarily cover post-exam 1 material. So I say primarily, like the questions are almost entirely based on things that we covered after the exam, but of course, a lot of these topics require an understanding of, what we covered in the beginning of the semester. Like we talked a lot about pre-training, scaling, things like that. Obviously, these all relate to the post-training that we covered afterwards. So, there might be questions that ask you to, for example, compare like a pre-trained model to a post-trained model with these conditions on this task. What do you expect would happen, and so on. So all that is to say that you won't be able to have a good conceptual understanding of the material we covered after exam 1 if you didn't already understand what we covered before. Okay, so on exam 1 we had a couple more coding related questions from homework 1. On this exam there will be a couple questions about homework 2, the one you just did, but none of them is coding related. So I gave you a ton of code in homework 2 as scaffolding, and you were basically asked to write a very tiny snippet of code and plug it in. There will not be any questions about the stuff that you didn't have to write. The questions are more conceptual in nature. It assumes that you know what the task was in homework 2 and asks you some questions on what do you think would happen if you did this with your reward and so on. So don't need to review the code in homework 2 to make sure you understand each individual line. That's not necessary, but if you did the homework, you should be able to answer the questions on the exam just through understanding what was going on in the homework. All right. Yes?
Are there any free responses?
No, sorry, no free response. I know I said we might have some, but multiple choice just makes the grading easy and we can get the grades to you super fast, so we decided to stick with that. Okay, so let me also just specify the cheat sheet again, because everyone loves to ask about the cheat sheet. 8.5 inch by 11 inch cheat sheet. You can use both sides and handwritten only. If you want to write on your iPad and then print that out, that's fine as long as you write it out by hand. All right, and last thing, which is a little different than exam 1, is that we noticed when grading exam 1 that the auto-grader would malfunction sometimes if instead of circling your answer, you wrote the letter of the answer next to the question, or you did a check mark or something like that. So I will emphasize this on Wednesday, but please circle your chosen answer. If you don't do this, then your exam might not be graded properly and you'll have to submit, what are those things called? Regrade requests, which ideally we would like to minimize. So please circle your chosen answer. Okay, any other logistics related questions about the exam? So just like before, there is another class that's in this room right after ours. So we will have a hard stop at 3:15 on Wednesday. Okay, great. So now what I wanted to do was just give a high-level overview of the topics that are on the exam and some kinds of things you may want to think about while studying in terms of what kinds of questions or what kinds of concepts and reasoning we're testing on this exam. So of course, the main differentiator behind this exam and exam 1 is that instead of talking about pre-training, we are talking about post-training. And so exam 1 was kind of heavier on the details behind the transformer architecture and things like that. This exam will not ask you any questions about transformer architecture or low-level questions about attention. Things like that are generally not the focus of this exam. Okay, so just to emphasize here, we are mainly talking about post-training. Like the majority of the lectures in the second half of the semester were related to post-training, right? Like SFT, instruction tuning, all the different RL algorithms, and then we started talking about evaluation of post-trained models, deployment of post-trained models in agents, how do you evaluate those, security risks of these things, and all of that. So we have a heavy focus on post-trained models. And, probably one of the biggest distinctions in how you do post-training is this tension between supervised fine-tuning and reinforcement learning, right? So we discussed kind of multiple methods for each of these. So if we go into SFT, right, we started out with discussing full model tuning, which is very similar to pre-training, right? Except the difference is in the data, right? In pre-training, you are really training your model over as many general text tokens as possible. In SFT, you're focusing on either, let me write this out here. You focus either on like a single task that you care about, and you collect a ton of examples of inputs and outputs for this task. Or, and what we focused on more, is this general concept of instruction tuning, right? Where you train your model on a diverse data set of many different tasks. So you have a natural language description of the task, like I'm going to give you a document. Summarize this document into 3 sentences, right? And then you have like an input, which could be any document, and the model has to apply that instruction to the document. And so like this concept of instruction tuning, we showed like if you take a huge pre-trained model and you do instruction tuning, the whole point is that this model will generalize to new tasks that were outside of your instruction tuning data set. So these two are they have opposite goals. Like the first one, you're trying to get a model that's as good as possible on this single task that you care about. In instruction tuning, you are trying to get a model that can generalize to new instructions that it hasn't been trained on, right? And so the latter is what we spent most of our time on, because we are interested in getting a model that can handle arbitrary user queries, right? And perform very well on all of those things. All right, so regarding methods, we talked about these parameter efficient fine-tuning methods, specifically LoRa, which is the most popular of these parameter efficient tuning strategies right now. Your homework was using LoRa also, by the way. And we also talked about prompt tuning, which is a slightly different version of this, where instead of modifying or like adding new parameters to the intermediate layers, like in LoRa, you have the low rank decomposition and you add it to the original parameters of the model. In prompt tuning, you learn like a couple new embeddings and you prepend them to the input token sequence. So you keep the model entirely frozen and you're just adding these new input tokens. So all of these methods here can be used interchangeably with any like data set of either single task or instruction tuning data sets. Okay, is that clear? Like SFT? So what are some limitations of SFT? Like we talked about a lot of limitations that kind of led us to pursue reinforcement learning. Yeah.
I mean, the big limitation, I believe, is that SFT only does not compare itself with like the model's own like outputs. It only compares it with like expert outputs. So
Exactly.
if the model gives like a wrong answer and then tries to go forward from there, it won't be able to do anything necessarily because it doesn't know how to deal with its own like imperfect.
Exactly. So we talked about two terms that were related to what you're saying, right? Which are teacher forcing and exposure bias. So in SFT, we are feeding the model with these human written outputs, and we're trying to increase the model's probability on those outputs. However, during the SFT stage, the model never sees any errors, right? Because it's receiving these high quality human demonstrations. It gets a perfect prefix and simply just predicts the next word. But at test time, we don't have a reference for the model to do that, right? We want the model to generate the entire thing by itself. And we know that the sampling process is kind of random. The model can make mistakes. And when it does, it quickly gets out of the distribution that it was trained on, like the human expert distribution. It won't know how to react to these weird errors that it's making, and its performance can degrade. So one of the motivations for switching to RL is to actually train the model to reward good generations from the model rather than from some human expert. Okay, what's another limitation of SFT?
It only produces one Y response for each context.
Yeah, so we train our model on only one reference per prompt, which is not a good strategy when you have open-ended generation tasks, right? Like if I wanted to generate a story, this single human-written story is not the only one that I could write in response to that prompt. And so I am not really covering the full distribution of valid and plausible outputs with SFT. Okay, so these are some of the key. Did you have another?
Can we say like you wouldn't learn from its mistakes?
Yeah, I think that's related to the, yeah. That's true. We can add that as a sub-bullet here. Data collection is expensive. So you can think about SFT as kind of requiring you to collect the reference outputs, right? In the case where they're written by humans. Whereas in RL, all you need is a set of prompts, right? Instructions. And then the model will generate some samples in response to those. You will score them somehow and then upweight the ones that are ideally scored highly. So yeah, these are kind of our motivating factors to explore reinforcement learning. However, before I transition, I should say also that despite these limitations, SFT is still like the first stage of post-training, right? It's not like we take our pre-trained model and immediately move towards RL. We always do, a round of SFT instruction tuning before doing RL. So why might that be? Because that's also important to understand. If SFT has all these limitations, why do we still do it?
Due to the generalization that it will give us compared to RL, that it will be more focused.
So theoretically, I could skip the SFT stage and take my pre-trained model and do RL on prompts from my instruction tuning data set, right? And I could reward the responses that actually follow the instruction and penalize ones that don't. I could theoretically do this, right? Nothing is stopping me from doing this, but why might not be? It might not be a good idea.
When pre-trained
Mm-hmm. Right. So you have a.
Yeah, from our experience with our project, not using not using an instruction to just without instruction tuning, the model is basically not able to follow instructions at all.
Yeah.
And
So I think you two are saying
with-
similar
yeah,
things.
probably.
A really important thing to understand is that the pre-trained model, if you just start with it, as you saw in your homework, like with the strict reward, right? Almost all of those samples got a reward of 0 or -1, right? Because they were not following the instruction at all. Similarly, if you use a pre-trained model for some complex instruction following task, it just does not have the capability on average to produce a good, like high quality response to that instruction. And so SFT is needed to kind of modify the behavior of the model such that it's better at following instructions. So you can think about SFT as kind of making larger changes to the model than RL. If you think about SFT, the reference outputs are from a different distribution. They're from like the human written responses, where it's unlikely that the pre-trained model will ever generate a response that is of the same level as these human responses. So you're actually trying to change the behavior of the model when it receives an instruction to follow that instruction, generate a well-formatted, high-quality response. RL is good if your model is already kind of good at doing the thing you want and you want to further improve it, right? Because in RL, you are still relying on the model's own outputs and scoring them. So as in the strict reward in your homework, if all of the responses in that group were bad, like all of the rollouts, you don't learn anything from that, right? So if the model is unable to follow an instruction and you don't do SFT and you're just doing RL, you'll have a ton of these kinds of groups where the outputs are just so bad that you don't learn anything from them. And so this is why SFT actually induces a behavioral change in the model compared to RL, which kind of just amplifies things that it already has these capabilities, if that makes sense. So that is kind of a higher level thing that is important to note. Yeah.
But if you only do RL, would they be able to still get like the generalization that we got from SFT?
So the question is, if you just do RL, will the model exhibit this like generalization to novel instructions or things like that, just like SFT? I mean, it's a tricky question to answer with certainty. Almost all post-trained models include SFT at the beginning, likely because if you just do RL on top of the pre-trained model, no matter how good that model is, you're just not going to get enough rollouts that actually follow the instruction for it to matter. That said, we did not discuss this at length, but there is now this concept of mid-training where during pre-training, they add examples of instruction following data in as like documents. And so this actually has some positive benefits for the generalization of the model. But yeah, the idea is that during pre-training, the model doesn't see that many instances of here's an instruction of how to do the task, do the task. And so if you just do RL on top of that, it may not know how to actually do those things. Yes?
I know in class we talked about another way to use the reward model using Raft, where we also use, that'd be like a second round of SFT.
Yes.
That's based on the model's generated outputs, right? Not
Yes.
human.
Could put that in here. That's a good point. So Raft is a way to kind of, it's kind of like an intermediate between SFT and RL because you are using the reward model and you are doing you're using the model's own generations as potential references, like the highest rewarded one. So in that way, it works very similarly to reinforcement learning. The only downside of Raft and any SFT method is you don't learn from, as you said, from negative feedback or your mistakes. And so in this case, if you generate a response that, so you generate like 8 different responses for one prompt, and you choose the one with the highest reward, and just SFT your model on that, you don't actually gain any insight from the other 7 responses, right? Whereas in RL, you would ideally learn from all of those responses. Like maybe some of them were terrible and you want to lower their probability so the model doesn't do that again, and some of them were really good. Or maybe all of them were good, and so you don't need to update your model, right? It's like more nuanced than SFT. But yeah, I should also mention, we talked about a different strategy related to Raft, which was best of n sampling. And here we didn't do any training at all, right? We have a reward model. We take a bunch of generations from our model, score them with the reward model, and just output the one that has the highest reward, right? So this is just a purely inference time way to use a reward model. I guess I shouldn't actually, this is a little misleading, because generally this is applied to on top of an SFT model, not on top of a pre-trained model. I could put it down here though. But yeah, it's important for you to understand these other options as well, like best of n sampling, reinforcement learning, Raft, SFT, so on. Just know what each of them does and what their drawbacks and benefits are. All right, let me just see on YouTube if no one has any questions. Okay, so let's start talking about reinforcement learning then. So here, I want to highlight again these kinds of different paradigms that we talked about, and so what are the differences between them. The thing we started with was RLHF, right, where we have this big data set of human preferences, and we train a reward model trained on human prefs. And we did this using the Bradley-Terry statistical model that basically allowed us to take a human preference judgment where you have some prompt, you have 2 candidate responses. Some human will say, I like response 2 better than response 1. And we turned this into a loss function that allows us to train a reward model, right? And so we talked a bunch about what reward models look like, right? Generally, reward models are just pre-trained SFT language model that we add like a linear layer on top to predict a single number, right? Then we fine-tune this whole thing on the data set of human preferences using our Bradley-Terry loss. So the reward model is actually a pretty bulky model, right? It's generally the same size as our policy model, which is the one that we're training. And we discussed why the reward model might need to be large and complicated, right? Why is that? Why do we need a big reward model generally? Yeah.
To understand, I guess, the nuances of language.
Exactly. Like the task of judging whether, like how good a response is to a given prompt itself is extremely complicated and requires a lot of language understanding and like understanding instructions and what is an appropriate output and what is not. As you say, it might just be as complicated as generating the outputs themselves. And so that's why like the best reward models, as we saw on that reward bench leaderboard, are all just fine-tuned versions of existing open weight language models. Okay, so it's important for you to understand like how reward models are trained, why they're so large, and how they slot into the RL algorithms that we discussed later on. Yeah.
Is the reward model, like the base reward model before going to the training, the same? Can it be the same as the model that you're trying to do RL on?
Yes. So it's very common to like you have your SFT model, right? Your instruction tuned model. You initialize that to be your policy model, and you keep updating it. But you can also train your reward model starting from that instruction tune checkpoint and just fine tune it on human preferences. However, like if you're training a small model, there's no reason for you to use a tiny reward model, right? You can, now there's so many off-the-shelf reward models that you can just plug in, which could be much larger than that model itself, yeah. Other questions on reward models? Okay. So before we dive into more RLHF, the competing thing that we talked about was RLVR, right? Reinforcement learning from verifiable rewards. And so this was best exemplified by the DeepSeek paper, and which also proposed the GRPO algorithm. So here, we're going to just avoid all the complexity of judging whether one response is better than another, which requires this expensive reward model. Instead, we're going to limit the number of tasks that we consider as part of our RL training. So this is typically done on like math, problem solving, or coding, where we can very easily assess the correctness of the model response, right? So on math problems, we can assess if the model got the right answer or not. On coding, we can assess if we execute the code the model generated, does it pass some unit tests, right? What is an advantage of this kind of reward compared to using a trained reward model, other than it's very cheap to compete? Yeah.
That was gonna be my answer.
Oh, yes. It's very cheap. We don't need a giant language model to do it.
I mean, a language model could potentially not do these tasks better, like math or coding, because they
Especially like coding, right? Language model would struggle, I would say, to actually like execute code and return the results. So true, it might be more difficult for a language model. Yes, so that is actually what I wanted to highlight by asking that question. So it is a lot harder to perform reward hacking, right? In the case of solving a math problem, and your answer is just 1 if the answer is correct, your reward is 1 if the answer is correct and 0 otherwise, it is very hard to even hypothesize a way to hack this reward, right? You're either correct or you're incorrect. Whereas with our reward models, there are many possible ways to accomplish reward hacking, right? You can, maybe humans prefer longer responses or responses that use more like fancy words or things like that. And so your model might latch on to these quirks of the reward model rather than, the true like underlying quality of the response. So we really, especially with like math and code, right? It's very hard to, hack a execution reward, although we did see some examples of that towards the end of the semester. Reward hacking is, reduced in these settings. So the disadvantage is, of course, you cannot define a verifiable reward for every task, right? If I ask you, what is a good verifiable reward for story generation, it's not at all clear, right? You actually need something that understands the generated story and assesses its, coherence or relevance to the prompt or things like that. So RLVR reduces reward hacking when it's used correctly, but it cannot be applied to all tasks. That's kind of the takeaway. Yes.
I know which angle think about the rewards that we are getting in both these cases. Is there any specific range that these rewards are giving?
Yeah, the rewards are usually normalized. Like -1 to 1 is a common range. But in RLVR, you generally see binary rewards very commonly. In some cases, you can have, like in your homework, for example, doing some reward shaping can have good big benefits as well.
Like, does it matter? Because eventually, if we consider like the GRPO sort of setting, it's anyways going to end up.
Yeah, in GRPO, it's always a z-score normalized, right? So it doesn't matter in that sense. Yeah. Yes.
So the GRPO models, like if let's say you have model, would it use like RLVR for some tasks and then RLHF for other tasks?
Yeah, so one thing I want to highlight is, we also talked about the algorithms, right? So let me write those down. Oops. So we have reinforce, right? That was the simplest one. And all of the methods that we talked about subsequently are based around reinforce, right? They're just more complicated versions that have different baselines, the whole clipping and trust region type thing. But, the core is still take a sample from the model, do an update that weights it by the log probability of the generating that response. So we talked about PPO, we talked about GRPO. Like these are the three main RL algorithms that we discussed. You can use any of these three algorithms for either RLHF or RLVR. So if you have a binary reward, you can still do PPO, right? You don't need a reward model. You can still use that objective. You can use GRPO with a reward model as well. So the distinction is really on this RLHF versus RLVR and not on the specific algorithms. It's just a little confusing because DeepSeek kind of came up with both RLVR and GRPO in the same, basically in the same paper, popularized both. So they're kind of used synonymously in on the internet right now. But it's not the case that you need to always use GRPO for RLVR and PPO for RLHF.
So would the DeepSeek GRPO model use RLVR for all math and code problems, but use RLHF for
Yeah, so if you read their paper, they do use first SFT, then they do RLVR, and yeah, they also incorporate other instruction following tasks, which I'm not sure if they use a standard reward model, but they're still using GRPO for all of this, and they probably just swap out the reward depending on the task. Yeah.
And just for my own clarification,
Yeah.
The rewards being z-score normalized or binary, is that only for RLVR, or is that for?
So in GRPO, we do z-score normalization of the rewards, and that's in the normalized across the group, right? So that's an algorithm level distinction. So here, GRPO does the z-score they call it group normalization. And they don't have, that forms their baseline, right, to calibrate the rewards. In PPO, we have this trained value function that is trying to estimate the baseline, right? So if we look at reinforce, we have the reward is this reward minus this baseline term, right? And so one of the differences between these three algorithms is how they handle the baseline term here. So in PPO, the baseline is actually prompt specific. So they train this value function to predict, based on the prompt and the current response so far, what is going to be the reward at the end of this response. So it's a you have to train this value function along with the training of the policy network. GRPO gets rid of the value function entirely, but you pay for that with additional rollouts, right? For one prompt, you have to do multiple rollouts, do the group normalization, and you may not learn from all of those rollouts, right? And you may not learn from all the groups. So generally, GRPO is preferable when you're in compute constrained settings because you don't have this value function. However, you still might have a reward model depending on like which paradigm, RLHF or RLVR, you're using it for. So it's definitely important to know the difference between these two things, RLHF and RLVR, what tasks they may or may not apply, and how each of these algorithms can be used for either of these settings. Yes?
So the value function will give us the baseline, will give us the R minus B.
No, the value function gives you the baseline. So the R comes from the reward model. Yeah. Yes?
So we talked about RAFT, RLHF.
Yeah.
My question is RAFT is kind of RLHF, and is RAFT using the Bradley model?
Yeah, that's a good question. So we talked about this RAFT, R-A-F-T, before we talked about RLVR. In principle, you can also do RAFT for RLVR, like if you have a verifiable reward. It's agnostic to the type of reward. So basically, if you have any way of ranking generations by the model, either with a reward model or with some verifiable reward, binary reward, whatever, you can use the RAFT to just do SFT on high reward samples. Yeah.
And it's not using Bradley model.
It could. Like the reward model could be trained with Bradley Terry on human preferences and be used in RAFT, but you could also use RAFT if you have like verifiable rewards that obviously don't use the Bradley Terry model.
I'm thinking the Bradley Terry model is pairwise, but RAFT choosing the best.
So RAFT is not. It just takes as input any reward model, right, and uses it to score. So the way it works is we have a prompt and we generate, let's say, 8 responses from the model for that prompt. So in best of n sampling, we would score each of those 8 responses with the reward model, right? And then we would pick the highest reward one and just show that to the user. So in this case, the reward model, choice of reward model is irrelevant. We can use our Bradley Terry trained reward model. We can use verifiable reward, whatever we want, as long as we get a score for each. In RAFT, it's basically the same setup, except when we take that highest scoring sample, instead of just showing it to the user, we actually train the model to increase the probability of that highest scoring sample. So it's like something you do after you have the reward model. It's not linked to the training of the reward model. Yeah. Yes. Yeah, so remember the Bradley Terry model, again, is only used to train the reward model, right? So the reward model, the input is a single example and the output is a score, right? And in reinforce and all of these algorithms, we're trying to maximize the expected score, right? Given any response from the model. So the Bradley Terry model comes in because the data that we have for training a reward model is in the form of prompt, winning response, losing response, right? And so we want to train a model that, like, given 2 responses and a prompt, can agree strongly with the human preference judgment. So that's the Bradley Terry model. If you look at the math behind it, that's the way that the training progresses in a way where we have this setup where we get a single score for a single response, but that score is meaningful in that you can use it to compare multiple responses. Again, like the training of the reward model is separate from the choice of the RL algorithm. So it can be plugged into any of these and it just gives you this score here, right? So it could be verifiable reward, it could be a reward model, or you know, the three algorithms here don't care basically where that comes from. Yes?
Is a value function where you take the prompt and the partial response, and then it predicts if you're on the right track?
Yeah, that's...
How does that get us the baseline instead of the reward? I thought that would have given insight into how the...
So the point is that so in like GRPO and reinforce, you get the reward at the very end of the response. And the way that you actually do the computations means you broadcast that reward to every individual token of the response. So you don't have any idea like at which point in the response did we go bad if we had a good response, or sorry, had a bad reward. The value function in PPO is essentially trying to do token level shaping of the reward, so that you know, if you made a mistake some part way through your response and your value function is strong enough to pick up on that, it can be like, okay, well at this point I predict that the overall reward will be really bad because we just did something, we repeated ourselves or we did something bad here. That's the idea. Training the value function is very difficult. As you can imagine, it is just like a reward model. It requires the model to understand, like, in relation to the prompt, how good is this current partial response. You know, it's just another model that needs to be kept in the GPU memory. So in GRPO, we don't have that, and we just broadcast the sequence level, the final reward, to all of the individual tokens. But this is like, I mean, not for this exam, but a very active area of research because you know, you're throwing out so much information if you just have this final sequence level reward, and if you could localize like different errors that are made in the response and, you know, add like positive or negative rewards to those specific tokens, you might be able to get a much more efficient learning algorithm. But it's not solved right now. Yeah.
But the prediction is basically like to give a, if it's bad, it would give a like large baseline for, I assume.
What do you mean?
Like if you're given some part of the response and it wants to predict.
Oh, yeah. I mean, we didn't actually talk about the training of that value function because it's a whole nother thing, but yeah, that's the general intuition. Yeah.
Just with, none of those three algorithms use a binary reward, right? Like a 0
They can all use a binary reward.
Okay.
Yeah. We didn't we only talked about like GRPO using a binary reward because we were talking about it in the context of RLVR, but there's nothing preventing you from using a binary reward with any of these algorithms. Yeah. Okay, good. Hopefully that clarified some stuff.
Yeah, your Slack is trying to do
This is so annoying. Okay. That's what you get for using UMD money to buy a laptop. They put all their admin software on it. Okay, so what else did I want to discuss? Right, so this here, this whole term we called the advantage, right? And when we were talking about RL, there was also the KL divergence penalty, right? Which intuitively was trying to keep the policy model, which is the one that we are currently training, from diverging too much from the SFT model. And why did we say that we wanted to do this? Like, why might this KL penalty be useful?
Hopefully to reduce reward hacking and keep like low
Right. So specifically, we talked about this term catastrophic forgetting, right? Which can happen if you like over optimize for your reward. You find some reward hacking behavior, and you get really, really good at producing high reward samples. But if you actually read those responses, they might be gibberish to a human. They might not be high quality, and they just found some strategy to maximize the reward. And so the idea is that if you put this KL penalty on during RL, you're going to discourage the model from straying too far away from the SFT model. So one thing to point out is that when we're doing RLVR, in many cases the KL penalty is dropped entirely. So why might that be the case? So we're doing RLVR, right? We have, let's say, a math problem correctness reward, and we're using some RL algorithm. In many cases here, we won't have the KL penalty term at all. Why might that be the case? Yeah.
Is it because we're generating a group of responses rather than just one?
So we are generating a group of responses, but all of the responses in the group could still, deviate far away from the SFT model. So, yeah.
Is it because it's already hard to reward hack, so we don't use it as stress bugs much?
Yes, exactly. So in this case, the reward is more robust to reward hacking, right? And so we might think that any kind of rollout where the model gets the correct answer should always be is an example of desired behavior and should be promoted in the model, regardless of if it deviates far away from the SFT model or not. So yes, that is the intuition behind. It's usually when you're doing RL with the reward model, like in RLHF, that the KL penalty is more important. So you can think about it as KL penalty usage if it is related to the expected difficulty of hacking the reward, if that makes sense. Okay, so the other thing that we talked about with PPO specifically was this clipping based on the policy ratio. And so one of the things that we kind of kept emphasizing when we were discussing RL is how unstable it is, right? We already have this reward hacking thing that could happen. We have this KL term to prevent us from deviating too far from our SFT model. But then, even within a single example, if we take too big of a gradient step, we could just mess up everything. Like our model's behavior, its performance on downstream tasks could massively degrade. And generally, RL is very unstable. So we, in PPO, discussed the clipping at each token, right, based on the policy ratio. So the policy ratio, we discussed this row I, where I is a particular position in the sequence, and that was equal to our probability yi of that token under our policy model divided by the probability under an older policy model. And so here, it is important to distinguish the old policy from the current one. This p theta old is not the same as p SFT, right? Generally, in PPO, unlike in reinforce, we take multiple gradient updates over the same batch of rollouts. So instead of just taking one and then moving on to the next prompt. The reason is we want to maximize the utility of those rollouts, right? It's very expensive to generate rollouts from a model. you have to do like token by token sampling, especially if you're doing something like GRPO and you have to generate like, 8 or 16 responses for a single prompt. It's expensive. Like even in your homework, that's a tiny language model. It has like 300 million parameters, and you can see it took 1.5 hours to get to like 75% accuracy. Imagine how that changes when you have 7 billion parameters or something like that. Like the cost of doing a rollout is expensive, especially as the number of tokens in the response increases. So the idea in PPO is that we want to try and make as good use of those rollouts as we can without kind of going too far and contributing to the training instability and making our model worse overall. So the clipping is basically a way to say, okay, for this token, I've already adjusted it enough. And now if I adjust it further compared to the model that generated this rollout, then I might be, contributing to some worsening performance. That's like the intuition, right? So we have this trust region, which is defined by the clipping, right? It's, defined by the policy ratio and this epsilon term. So we do clip of the policy ratio to lie in between 1 minus epsilon and 1 plus epsilon, where this epsilon is generally something small, like 0.2. And so when our model probability for a token lies outside this trust region, we have to take a call on whether we want to do an update or not, right? And that's a function of the advantage. So if the advantage is positive, we might want to increase the probability of that token, but to a point, right? We don't want to increase its probability when the policy ratio is too high. On the other hand, if the policy ratio is lower than the minimum threshold, but the advantage is positive, that means that our current model is actually putting lower probability on this like good token than the old model was. So we want to still increase the probability of that particular token. So I won't go over it here, but we did draw out that plot of how the advantage behaves in these different clipping ratios and thresholds. So you should expect some questions on, okay, the policy ratio is this, the advantage is this, what happens? Like what are we trying to do with this particular token, right? Which generally just follow from that plot. I also, there was a question on Piazza that noted some errors in the notes on the clipping, so I clarified those on Piazza. But like you're not going to do clipping if the model falls. Like if the policy ratio falls between these thresholds, obviously there's no clipping applied. The notes were a little confusing because they showed like what would happen if the policy ratio were clipped versus unclipped. So make sure you understand the different cases that could arise when like the advantage is varied, positive or negative, and the policy ratio is also varied. Yes?
So during backpropagation, like does the policy ratio still exist, like and still used like as a scaling factor?
Yeah, actually in PPO, the only way that the policy is updated is through this numerator here, which is the probability of the token under the current model. Yeah, so the policy ratio is essential for backprop. That's why when we clip, if we clip the policy ratio, this numerator is no longer used, right? We've just set this to a fixed number, and so we don't actually have any gradient flow through the numerator to the current policy model. That's a good question. Yeah.
So does the denominator ever change?
Yeah, so the denominator is basically the parameters associated with the model that generated those rollouts. So the very first iteration of gradient updates on the current batch, the policy ratio is 1 because this p theta old is the same as p theta. Once we make an update, now we've changed our parameters, right? So now those two things are different. But yeah, p theta old is always like the model that actually generated those rollouts. So it's just a few gradient steps away from the current policy model at max. And generally it's a hyperparameter, like how many steps do you want to take on a particular batch? Something like 4, I think, is the default. Yes? Yeah, essentially, like PPO is very similar to reinforce. Like you're still computing this advantage, blah, 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 but you're doing this clipping thing. And generally, remember that in PPO, the KL term is also kind of rolled into the advantage. But yeah, everything is basically the difference is the clipping and multiple steps on the multiple gradient steps on the same response. Okay, so yeah, and you know, GRPO is related to your question. Moving from PPO to GRPO is also very straightforward. We keep all of the clipping stuff. So PPO to GRPO. Keep all the clipping policy ratio stuff, but we remove the value function. And our advantage computation is also different. So here it's this group normalized term. This is the mean reward of the group, and this is the standard deviation. So this whole thing is called group normalization in the DeepSeek paper. And now, like, we drop the value function when we move from GRPO to PPO. If we are using GRPO for RLVR instead of RLHF, we additionally drop the reward model, right? So if we're doing GRPO with verifiable reward, we only have to keep the current policy model in our GPU memory. However, if we're using the KL penalty, then we will need to keep a copy of the SFT model in the GPU as well, right, to compute that penalty. So if we drop the KL penalty as well, that frees up another, giant language model that we don't have to store in our parameters. And all of that saved memory we could use to, do more rollouts or do this on bigger models and things like that. Yes?
So if you use RLVR here, our rewards would be binaries.
They could be like in your homework, right? The rewards were not binary, they were like numeric, but you had defined some rules on when the reward is this particular number. Yeah. Other questions? Okay, so let me just write out some of those things. So GRPO, maybe the easiest thing to write out, GRPO plus verifiable reward plus no KL term means only have to store one big model in GPU memory, which is the p theta. So if we change any of these things, if we add the KL penalty, we will need to store the p SFT. If we add the reward model instead of the verifiable reward, then we will have to store the reward model. If we switch to PPO, then we will have to add a value function. So those are kind of the, yeah.
Shouldn't it be two, p theta and p theta old?
Yeah, p theta old, generally, like, you already have the probabilities you need because you generated the rollout itself, so you don't have to actually store those parameters. Because you used p theta old to generate the text, generate the response. So you already know the log probabilities of those tokens from p theta old.
I'm curious, like when we use this like trainer,
Uh-huh.
high level trainer, do they implement it this way or they actually put two at to the memory at the same time?
No, they would not do that because there's no reason to. Like, you already have the, like, p theta old generated these rollouts, right? It was the, and then your current policy is the one that you're updating. So you can cache p theta old's probabilities and just use them in this computation. No need to, yeah.
When you say p theta, that's the softmax of the null.
Sorry, p theta, I should clarify. This is our current policy model. So it's the entire transformer that we are optimizing. It produces, yeah, the p theta is the final softmax probability distribution. But, you know, that's just what we're using to refer to the whole model. Do you have a question? Okay. Yeah. Yeah.
What's that? Like, that's the log. Both of these terms are log probability.
The policy ratio is on the raw probabilities. Yeah. 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 So p theta old does not change in the, to clarify, p theta old will change from batch to batch, but within one batch it's the same. It's the first iteration of that batch, like before the first update, if that makes sense. Yeah, so that's when p theta old diverges from p theta. Like when you do another update on the same batch, then your p theta will now be different from p theta old. Yeah.
So when p theta old, like let's say a batch is done, does
Yeah.
p theta become the next p theta old?
Yeah, that's right. Great. So other questions on this?
The p data is the same within batch, but it's different to other batch.
Yeah, because p theta is always like your most current model, like after the very latest update. So like PSFT is the model that we started with before any sort of RL, and p theta old is the model that just generated all the rollouts that we're about to perform updates on.
But in one batch, we might update it 4 times. But
Right. So p theta old is always the first, and even on the third step, p theta old is still the first. Yeah. Okay. Great. Let's see. Oh wow, I think these are like the most complicated topics, so it's good we spent time on them. The one thing that I do want to mention regarding GRPO that we haven't talked about already is the, so essentially RLVR can incentivize thinking or reasoning. And we saw this special prompt format, right, which was like, you have some prompt and the model's response is like, think, blah, 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 and think, and then it might produce its answer, 32, and answer. So this was also pioneered by the DeepSeek paper, right? And they showed that if you're using RLVR with like math problem correctness and you maximize the reward, but you enforce this prompt format, you actually see that over time, as the reward increases, the length of the reasoning chain right? So whatever is in here is generally called the reasoning chain. Often you'll also see it referred to as a thought. So the length of this thing is increasing, and that led to the conclusion that increasing test time compute, which is, if the reasoning chain is longer, you're spending more compute at test time, improves models' performance on a bunch of different tasks. So again, this is an important concept that we covered, and we showed a bunch of those evaluations that suggested this. So okay, what else did we talk about in the last minute here? We talked about language model evaluation, right? So we had like Blue versus LLM judges and things like that as metrics. We also had like static data sets versus dynamic, like evolving benchmarks. What else did we do? What's that?
RAG.
Oh yes, we did RAG, we did agents, so those are all related like tool use. So in agents, we have like a dynamic controller LLM that decides when to call tools and which tools to call. We also, in our evals lectures, talked about data contamination. So what happens if you evaluate a model over some data set that was already present in its pre-training? It's going to not be a good measurement. That's why we kind of motivated dynamic evaluations. I guess as a last thing, we talked about security. So there's a bunch of different attacks like jailbreaking, membership inference, prompt injection, data poisoning. You should know roughly what all of those things do. And the final lecture was on memorization. So we talked about the mem quantity and the capacity of a model. So you should understand what those things are and what it means when the model's memorization capacity has been reached. How does that impact generalization versus memorization, and so on. So, all right, good luck on the exam. I will see you here on Wednesday. And since I guess this is the last time I will be lecturing to you, hope you enjoyed the semester. A lot of this stuff is, super new, so hopefully I can reuse a lot of this stuff next time I teach it. But the fact that I couldn't reuse a lot of my last year's materials for this semester indicates that maybe that is not going to happen. But anyway, I enjoyed it and also learned a lot myself. So yeah, good luck with your studying and your projects also. Good luck with your projects too.
May I ask some questions?
Yes.
Of notes? Here.
Yeah.
Here that we use the RXY, shouldn't we also include the baseline here?
Yeah, so the expectation is over the reward, because if you do this computation, the baseline doesn't actually affect the result of this expectation.
I see. So if you have the baseline here, the result will be the same.
Yeah, so you have to choose a baseline that doesn't depend on this p theta, and if you do that, you can write out the math and see that it doesn't actually impact this. So you're always maximizing the expected reward. You can subtract a baseline and not change the. Yeah.